When I first learned calculus many years ago, I seem to remember going straight from limits to finding derivatives using the power rule of calculus. But in this later go-around at learning calculus, this time to prepare to teach the subject, I took interest in the definition of a derivative. The most fundamental relationship on a coordinate plane is perhaps the equation of a line, and here is the line we'll be first evaluating in blue. We can find the slope or rate of change of this line by using a rate of change formula. The formula shown in most early algebra studies is this one: m for slope equals y2 minus y1 over x2 minus x1 is the change in y divided by the change in x. Verbally, slope is the answer to the question: how much does the value of y increase when the value of x is increased by 1 unit? But as we move along towards and into calculus, you will see yet a different version of the slope formula, and it's this one: m equals delta y over delta x. Delta y is the change in the y value, and delta x is the change in the x value. You may have seen this version in physics. Now we can pick out 2 points on the line. I picked these 2 points shown with the arrows, but on a line, does it matter which 2 points we choose? No, it doesn't. The coordinates of the 2 points are 7, 8 for the first point, which we call x1, y1, and 17, 15 for the second point, which we call x2, y2. The change in y, or delta y, is going to be this distance represented by the green line segment, the difference of the top y value, which is 15, and the lower y value in our second point, 8. And this vertical distance, or difference, is 7. And the change in x, or delta x, is the difference between the x value in the second point and the x value of the first point, and this difference is shown by the orange line segment below. And this value for delta x is 10. So for this blue line, the slope is 7/10, 0.7 in decimal form, or 70% in percentage notation. Well, now let's look at this function, the parent quadratic function f of x equals x squared, or y equals x squared. We just looked at the slope of a line. What is the slope of this function? A function that curves has no fixed number for slope. We can use a tangent to the curve to indicate the slope of this curve at a given point, and here is a red tangent line on the left side of the parabola. This line has a negative slope. Maybe it looks like it's around -3 or so. But this isn't the only slope of this function. Here, the tangent line touches the bottom of the curve. At this point at the bottom, or minimum, the value of the slope of the curve is 0 because the slope of a horizontal line is 0. Now we'll try to look at the slope of the curve on the right side where x equals 2. If we wanted to, we could calculate the slope of the drawn tangent line by finding 2 points on this red line and then using the slope formula. However, the slope of the drawn tangent line would only be an estimate, as it would be subject to the limitations of our human error in drawing and interpreting. One thing we can do is fix 2 points to estimate the slope at a single point on the curve. We establish our slope to estimate by starting at the point where we want to evaluate 2, 4. Along the x-axis, we're going to add a certain distance, which we'll call h, and that's the length of the green line segment along the x-axis. So this distance from the origin going along the x-axis is 2 plus h. And from 2 plus h marked on the x-axis, we'll go up to the curve. And the coordinates of this new point on the curve are 2 plus h, comma, f of quantity 2 plus h. f of 2 plus h, or quantity 2 plus h, just means the y value for an input to the function of 2 plus h. Using these 2 points, we can create a secant line. A secant line is a line constructed from 2 points on a curve. The one drawn here is in red. I hope you can see that the red secant line is definitely steeper than the slope of the curve at the point 2, 4. In fact, here's the drawn tangent line from earlier, this time in blue, so they can be compared, the blue line and the red one. In this graphic, 2 plus h seems to be a little over 4 on the x-axis, so h seems to be a little over 2, and again h is the green horizontal line segment along the x-axis. In this next graphic, we've just made h quite a bit smaller, so that now 2 plus h seems to be about 3. Look how things change. See how much lower the point 2 plus h comma f of quantity 2 plus h is on the curve. This new secant line would still be steeper than the tangent line at x equals 2, but much closer to its true value. We cannot even see space between that new secant line and the curve, since they are now much closer in value. Now here's the crucial point in determining the slope of a curve. As h becomes infinitesimally small, the slope of the secant line will be exactly the same as the slope of the tangent line on the curve at the point 2, 4. In fact, when this happens, when h becomes infinitesimally small, the secant line becomes the tangent line. Here, using the slope formula, this is what we see. Remember that the slope formula is m equals y2 minus y1 over x2 minus x1. And with the points we have here, the slope formula filled in looks like this. M equals f of quantity 2 plus h minus 4 over 2 plus h minus 2. This is just placing our x and y values into the slope formula. And in the denominator, 2 minus 2 cancel to equal 0. So what we're left with is f of quantity 2 plus h minus 4 over h. If we can make h get smaller and smaller to the point where h equals 0, we would have the slope of the curve or the tangent line at the point 2, 4. But if h is 0, what happens to m? Can you divide by 0 in math or in algebra? No, we cannot divide by 0. If you are taking beginning calculus now, and this is where you are in the course, you've just been covering limits. If you ask why we're going from limits to this, I'm about to show you the reason why. We will apply the concept of limits. Here it is. M is equal to the limit, as h goes to 0, of f of quantity 2 plus h minus 4 over h. And when you see this limit defined generically without specific numbers for x and y, this is what it looks like. And this look is called the definition of a derivative. The definition of a derivative is the limit as h goes to 0 of f of quantity x plus h minus f of x divided by h. I bring this up this way because in your calculus career you may see something in this format. It's really just a slope form taken to the limit. When you see the limit of a denominator going to 0, just try not to be intimidated. Even though I've seen h used, delta x can be used, and here is the delta x form of the definition of a derivative. It's the limit as delta x goes to 0 of f of quantity x plus delta x minus f of x all over delta x. Don't be intimidated. We'll go back to the problem we've been working on, and that's to evaluate the slope of our curve at the point 2, 4. Here's our problem again. Our next step is to replace 2 plus h into our function f of x. So what this becomes is m, or the slope, equals the limit as h goes to 0 of quantity 2 plus h squared minus 4 over h. Now we'll work on the left at the top. Expanding the squared term, we have m equals the limit as h goes to 0 of quantity 2 plus h times quantity 2 plus h minus 4 over h. So that quantity 2 plus h, that's like x. And so another quantity 2 plus h, that would be like x squared. And multiplying out the binomials, we have m equals the limit as h goes to 0 of 4 plus 2h plus 2h plus h squared minus 4 over h. 4 minus 4 cancel in the numerator to equal 0. We bring down what's left, combining 2h plus 2h, so we have m equals the limit as h goes to 0 of 4h plus h squared over h. Now we can divide 4h and h squared in the numerator by the h in the denominator, so we're left with the limit as h goes to 0 of 4 plus h. And this limit equals 4 as h goes to 0. So this is the slope of the curve at x equals 2, which is the slope of the tangent line at that point. The great thing about the definition of a derivative is that it shows in a step-by-step manner how the slope of a line at a point is really determined using limits. Later on, Soon, we will learn to use the power rule of derivatives that will make such calculations a lot faster. But I hope you won't forget that the power rule that makes things easy really begins here with the definition of a derivative. One of the most important things to get out of this lesson is to be prepared for the form of a definition of a derivative. The definition of a derivative is just using the concept of using the slope formula along with the principle of limits to find the slope at one point. This has been Definition of a Derivative. Thanks for viewing.